Hello, and thank you for joining us today for the Download Community Tech Talks. These are Tech Talks for the HPCC Systems community by the HPCC Systems community. And this episode, episode 16, is a very special edition because we've got our 2018 summer interns with us. So we're thrilled you decided to join us today, and I know you're in for a bunch of exciting presentations. So to go through some simple ground rules, number one, please share. So while you're on with us today, or if you're listening after the fact, please let people know. Use the hashtag HPCC Systems Tech Talks. And please ask your questions. We will answer as many as we can following each speaker. We will also have polls throughout the presentation. So if you don't see the polls, please look at the bottom of your screen. If you still don't see them, exit the full screen mode, refresh your screen, and they should be there. Also, we welcome your feedback, and please do rate us today before you leave. And if you'd like to be one of our featured speakers, or if you have any insight for us, all you'd like to share, please send us a note. techtalks@hpccsystem.com. Very exciting news. We've got our 2018 HPCC Systems Community Day happening here in Atlanta on October 8th. So just coming up in a few months. We're very excited that registration is now open for the external community, so we hope that you'll have time to join us. Please go to our website, which is hpcc.com/HPCC Summit 2018. You can find the registration information there. Please do bookmark this page because even if you can't attend in person, we welcome you to join us via live stream. So watch that page and information will be coming available over the next few months, but registration is open today. All right, so for today's guest moderator, it is the lovely Lorraine Chapman. And Lorraine, we are so happy that you're here with us. Lorraine has worked with software developers over the last 20 years, and she is just extremely instrumental in working with our technologists here. She also leads the internship program for HPCC Systems, so arranging for mentors, working hand in hand with each one of our interns to make sure that they have a good experience here and that they're progressing forward. And so we're thrilled that Lorraine is here today, and she's going to be your guest moderator throughout the event. So Lorraine, I'm turning it over to you.
Thank you, Jessica, for that lovely introduction. I'm just going to forward the slides on here. We've had 8 interns join us this summer. And today we have 4 of them presenting about their projects. I'm going to move quickly through some introductions so that we can get to the presentations, which is why we're all here today. So the 2 students featured on your screen right now will be speaking about their machine learning projects. Shah Mohammed Hamdi is a PhD student in computer science at Georgia State University. And Robert Kennedy is a first-year PhD student, also in computer science, at Florida Atlantic University. So also presenting today, we have 2 students who will be taking us through the progress they have made on their platform-related projects. So we have Aramis Tanalis, a high school student from American Heritage High School in Florida, and Saminder Vijayaratne is a master's student of computational science and engineering studying at the Georgia Institute of Technology. So let's move to our first presenter. So application onto our program is by the submission of a project proposal showing the work needed to complete the project and a plan for what needs to be done each week. So while students may choose a project from the list we provide, they can also suggest a project of their own as long as it leverages HPCC systems in some way. And this is exactly what Hamdi did. Hamdi is mentored by Roger Dev, who manages the HPCC Systems Machine Learning Library project. And Roger was very keen to have Hamdi join the team to implement feature selection for our machine learning library. So without further ado, let's find out more about Hamdi's project and the progress he has made so far. So over to you, Hamdi.
Hi everyone, I am Shah Mohammad Hamdi. In this summer, I'm working on the dimensionality reduction techniques using parallel block basic linear algebra subsystem library under the mentorship of Roger Dev. Here is my presentation outline. In the beginning, I will talk about the basic concepts of principal component analysis or PCA. Then I will talk about our PB+ implementation of PCA, an existing MATLAB implementation of PCA with which we test our algorithms, and two already implemented models, which are the implicit Cholesky factorization based method and eigendecomposition based method. Finally, I will conclude my talk by telling about the helper functions that we have developed and some current and future works. PCA is one of the most popular and widely used dimensionality reduction techniques. Nowadays, because of the advent of data collection technologies, we face high dimensional data in any type of data-driven analysis. When each sample of interest of a real-world problem is represented by a vector consisted of many features, often in hundreds or thousands of features, a high-dimensional dataset is created. Such high dimensionality of data increases the complexity and results in poor performance when they are fed into any type of supervised or unsupervised learning task, whose common goals are predicting unlabeled samples or clustering similar samples. The problem is well known as the curse of dimensionality. PCA is a very useful tool for getting rid of such curse of dimensionality. In addition to reducing the complexity of learning algorithms, PCA is also used for the visualization of high dimensional data to 2D or 3D space and data compression also. There are many theoretical solutions for PCA. The most popular theoretical approach is the singular value decomposition or SVD of the covariance matrix, where the covariance matrix is the pairwise similarity of the given features. SVD of the covariance matrix gives the principal components, which are the dimensions on which data variance is maximized. Parallel computation of PCA is important because it enables us the simultaneous PCA computation of any large data sets, and also because of the fact that the covariance matrix can be huge and the SVD can be computationally very expensive for large covariance matrices. Here we show one example of how PCA is used for data compression. In the left image, you see 100 samples from the phase dataset of the University of Massachusetts. The whole dataset contains 13,000 phase images, where each image is resized into 32 by 32 pixels. Before running the PCA, each image is represented by a vector of 1,024 features. In the middle image, you see the visualization of the top 36 principal components. Instead of using 1,000 features, the projection of the images to these top principal components leads to an excellent compression. In the rightmost image, you see the reconstruction of the images using only top 100 principal components, which is a proof of 10 times data compression. My first question for you is, can PCA be used for improving the performance of classifier or a clustering algorithm? Please select the answer on your screen, and the result will be shared at the end of my talk. Okay, let's continue. PBBLAS already have PBBLAS or parallel block basic linear algebra subsystem is a library for HPCC platform. This library helps the parallel computation of basic matrix operations. The functions of this library handle the matrices in a special format called layout cell. Layout cell format has 4 slides: WIID for work item ID, X for row index, Y for column index, and V for the value. We have shown one example of matrix representation in regular format and layout cell format. In a nutshell, the regular matrix is transformed into a table of 4 fields. PBBLAS already have a rich set of basic matrix functions, such as AXPY for matrix addition and subtraction, GEMM for matrix multiplication, GetRF for LU factorization, QuotRF for Cholesky factorization, Hadamard's product for element-wise multiplication, TRSM for triangular matrix solving, and also some functions for transposing and scaling the matrix. The goal of our project is to develop a parallel version for PCA in HPCC platform by leveraging these PBBLAS functions, which means by using them as building blocks. To test our parallel PCA algorithms, we compared our test results with a MATLAB implementation of PCA in an example toy dataset, which consisted of 50 samples and 2 features. In the left figure, you can see the visualization of the data points in 2D space. In the second figure, you see the intermediate results, which are the covariance matrix, the singular values and singular vectors after SVD computation. The singular vectors represent the principal components. It is easy to see that one singular value has high value, while the other one has a low value. It represents that the variance captured by the corresponding singular vectors or singular or principal components. In the third figure, the first and second principal components are shown as straight lines. Note that the first line goes through the maximally variant axis. Finally, in the fourth figure, we show the projection of the data points from the original 2D space to the first principal component. By this projection, the dimensionality has been reduced from 2 to 1. Now, I will focus on our implemented parallel models for PCA. The first one is based on computationally less expensive Cholesky decomposition. Cholesky decomposition is a matrix factorization method which factors a square matrix into a lower or upper triangular matrix and its conjugate transpose. Cholesky decomposition was already implemented in PBBLAS as a function named QuotRF. In this implementation, we calculate the covariance matrix at first and then do the Cholesky decomposition and finally go through the loop of algorithm 2 that you see in the left of the slide. We initialize the matrices of left and right singular vectors by identity matrices. Then, in the for loop, we do QR decomposition and update the matrices of holding singular values and vectors. QR decomposition was not implemented in PBBLAS before, so we tried 2 approaches. Firstly, we use the QR decomposition function of ECL-ML, and secondly, we coded the QR decomposition for PBBLAS and used it in the for loop. While the first approach is actually a serial operation, we tried both approaches for our validation. The convergence of the loop is done by the Frobenius norm of consecutive Li matrices. Here, we show how our implicit Cholesky factorization-based approach produces the almost same result as SVD-based MATLAB implementation. you see the covariance matrix, singular values, left and right singular vectors of our implemented model and that of the MATLAB implementation. We found that the implicit Cholesky-based factorization based method takes long time for convergence and the singular values deviate from the actual result. Left and right singular vectors are also not the same, what was expected. The results motivated us for working on another implementation model. In this model, we just followed the architecture of the PCA implementation of ECL-ML. In ECL-ML, the matrices are in element type, which slightly differs from the layout cell format of PBBLAS. We modify the code so that the matrix formats are in layout cell format and customized all the necessary functions. This approach calculates the covariance matrix in the beginning and then does the singular value decomposition, which is the eigen decomposition of covariance matrix. The eigen decomposition uses QR decomposition in a convergence loop. Here, the convergence is made by L2 norm of the vectors. While implementing this model, we have developed PBBLAS functions for SVD and eigen decomposition. Here we show the similar type of test of our eigen decomposition based approach and the MATLAB implementation. Unlike the implicit Cholesky based approach, this approach converges very fast and generates the exact same singular values. The left and right singular vectors are also exactly the same. My second question for you is, if we do SVD on a symmetric matrix, will the left and right singular vectors be the same? Please select the answer on your screen. The results will be shared at the end of my talk. While developing the parallel PCA using PBBLAS, we also implemented some very important functions, which are used very frequently, almost in any machine learning project. Machine learning libraries of Python, R, and MATLAB have almost all of these functions implemented. These functions are easy to implement, but very useful for implementing any machine learning model. Some examples are L2 norm of the vectors, Frobenius norm of the matrices, identity matrix creation, construction of vectors of 1 or zeros or any constant value given the vector length, dot product or cosine similarity of two vectors, householder reflection operation, and so on. Before this project, PBBLAS library had only two matrix decomposition algorithms implemented. They are LU decomposition and Cholesky decomposition. Now we have added SVD, eigen decomposition, and QR decomposition. Moreover, we debugged some existing PBBLAS code, such as fixing the sparse matrix handling of AXPY function. As the conclusion of this talk, I want to say that the parallel PCA implementation in HPCC platform is finished, and we have tested our implementation with 3 datasets. First one is the TOY2D dataset. The second one is the Friedman-Fries dataset with 4 features and 1,000 samples, which was used for the testing of the linear regression bundle 2. And the third one is the 100 samples from UMass phase dataset, which has more than 1,000 features. Currently, me and my mentor are working on the kernel PCA implementation for non-linear dimensionality reduction. where we are implementing different well-known kernels such as linear kernel, Gaussian or RBF kernel, polynomial kernel, sigmoid kernel using PV+ function. In future, we also look forward to implementing some common feature selection algorithms such as Fisher, mutual information, minimal redundancy, maximal relevance, and Laplacian score. And that's all from me. And thank you very much for listening. And I'm going to answer your questions very soon. Thank you very much.
Thank you, Hamdi. So while you take a moment to look at the questions and prioritize them, we're going to take a look at your poll questions. So on your first poll, the question was, can PCA be used for improving the performance of classifier or clustering algorithms? So 70% of you on the webcast with us today said yes. 30% weren't sure, but nobody said no. So I suppose that's a good thing. 70% say yes. And looking at your second question, which was, if we do SVD on a real valued symmetric matrix, will the left and right singular vectors be the same? And we've got an even split down the line. So 33% say yes, 33% say no, and 33% say not sure. So that's a really, really interesting result. All right. So Hamdi, are you ready for your question?
Yes, I'm ready.
All right. So here's our first one. Can you tell us about the helper functions you coded for being used in PV+? Okay,
the answer is I have customized ECL-ML's eigendecomposition, singular value decomposition, Kewer decomposition, and householder reflection for the use in PV+. Additionally, I have developed several utility functions on PV+ that can be used in any machine learning project, such as the functions for computing the LT norm of a vector, provenance norm of a matrix, identity matrix of a given shape, vectors of ones, zeros, or any constant value when the length is given, dot product of two vectors, and so on. So those are the helper functions that we have already developed.
Okay, perfect. And it looks like we have another question here. Okay. Is it a classical PCA approach, which is actually the eigendecomposition of the covariance matrix, modified with PV+ library, or have you developed some other approach for PCA calculation from literature?
Okay. We have implemented both approaches that your question mentions about. Firstly, we learned about the classical PCA implemented in ECL-ML, which is the singular value decomposition or eigendecomposition of the covariance matrix, and modified it with the PV+-based parallel matrix operations. In this approach, the results are exactly the same as the MATLAB implementation. Secondly, we have followed the implicit Cholesky factorization for SVD from a published paper. In this approach, we calculate the Cholesky decomposition of the covariance matrix by the existing PV+ function, and then we used the Kewer decomposition function, customized for PV+. In a convergence loop, in the end, we get the singular values and singular vectors, which are almost the same as the MATLAB implementation.
Okay, let's see. It looks like there's another question here. Where has PCA found the most value in real-world big data applications?
Okay, PCA found the most value, I think, almost in any kind of supervised and unsupervised learning task, but still I believe that in the image community, it was used most frequently. For example, there is a term called eigenfaces. It was invented by some MIT researchers in the 90s. So usually the images that we take in our cameras and other sensors, it is very high dimensional. Okay, just think about the examples that I have talked about. It is just a 32 by 32 pixel image. It was flattened into a 1000 dimensional feature space. So you need to reduce this dimensionality by some way. So that's why PCA is a very well-known technique for reducing this dimensionality. And for visualization, there was some other techniques like TSNE, but still PCA prioritized the domain of the dimensionality reduction was still now. PCA is an old technique, but still it is used very, very frequently. In the not only in the image, the PCA is also used in the speech recognition and text mining too. So that's it. I think I have found your answer.
All right, perfect. All right. Let's see. It looks like we might have time for one more question here. So Hamdi, yeah, here's one. Are you planning to implement any other dimensionality reduction methods?
Yes, we are. PCA is a linear dimensionality reduction technique. Right now, we are focusing on the non-linear, that means more powerful dimensionality reduction techniques. And we have kernel PCA for now. Okay, there are different kinds of kernel that was developed since the 80s, like Gaussian kernel, polynomial kernel, sigmoid kernel, etc. And right now, we are focusing on implementing the kernel PCA so that even the clustering problems like two-moon problem or the nested circle problem, okay, those are solved by those are not solved by the linear PCA, but those are solved by the nonlinear PCA. So we are focusing on the kernel PCA for that.
All right, wonderful. All right, Hamdi, thank you so much. We actually have several questions still in the queue here, so but we're running out of time, so I'm sorry that we can't get to all of those today. But please keep them coming in. I think it's really important for our interns, so we have several today. Please make sure you're still sending questions in. I apologize that we can't get to all of them. So Hamdi, thank you so much. And at this point, I'm going to turn everything back over to Lorraine so that she can introduce our next presenter. Hello, Lorraine. Are you able to? I think you might be on mute.
Hello, can you hear me?
There you are.
Okay.
All right, wonderful.
Thank you, Hamdi, for a great presentation. It's now time for us to meet Robert Kennedy. Robert works with Dr. Taghi Koshkoff-Tar, who we know well from previous collaborations via our academic program. They're working together on another project relating to multimedia big data processing using HPCC systems, which may benefit from the results of this internship project. And we also believe these results will be useful to another student who's working on a project involving TensorFlow and HPCC systems, which is currently underway at Imperial College London. But the results of Robert's intern project will be of use to anyone who intends to use neural networks with HPCC systems. Robert is co-mentored by our HPCC systems colleague Tim Humphrey alongside Professor Koshkoff-Tar. This is a really interesting project, so now let's hear more about it from Robert.
Hi, thank you, Lorraine. My name is Robert, and I'm a summer intern for HPCC Systems. I'd first like to thank my mentors, Tim Humphrey of LexisNexis, and my professor and advisor, Dr. Taghi Koshkoff-Tar. Without their help, this would not have been possible. So my project is to extend HPCC Systems' deep learning capabilities. Oh, I'm sorry. Let me start with a quick poll. If you use machine learning, are you using HPC systems for building the models or not? HPCC. Please answer the question on the screen, and we'll go over the results at the end. Okay, here's some background. Again, my project is to extend HPCC systems' deep learning capabilities by creating a new machine learning library. Of course, it will be open source and put onto GitHub for anybody to use. The library will leverages ECL code with the open source Python library TensorFlow. TensorFlow, we'll go over briefly later, is made by Google and is a very popular open source deep learning library. Currently, HPCC does have some common machine learning algorithms via some different libraries, but is lacking the more complex and contemporary algorithms such as deep learning. So that's what my project aims to fix. So this presentation, we'll go over the project goals, the problem statement. We'll give a brief introduction to neural networks and how they train. We'll just touch on that real briefly. We don't have too much time, but it's be very quick. And we'll give an introduction to the parallel deep learning methods and techniques, which is kind of the meat and potatoes of the project. We'll go over the technologies used in the implementation. We'll go over there'll be a code example. We'll go over some ECL code, Python code, and we'll touch on the other open source Python libraries that are used. I'll detail the implementation itself, and I've done some statistical analysis that validates the implementation, and we'll go over that as well. And we'll conclude with some possible avenues for future work that can extend upon this work to make it better. So the main goal of my project is to extend HPCC by providing it a deep learning library using existing open source deep learning libraries, specifically a distributed parallel deep learning library. I know it is possible to train on a single node, which is quite easy. But this project aims to give a distributed parallel training environment, which is quite a bit more complex. The goal is to use TensorFlow within the HPCC environment. In addition to TensorFlow, I've used other libraries, which are all open source, but the main one being what's called Keras, K-E-R-A-S. We'll go over that briefly later as well. So HPCC provides, of course, the general cluster environment. The ECL compiler handles the data, and the distribution of the data, and it also handles the Python runtime via the PyEmbed plugin. I'm using Python version 2.7. That or version 3 should be fine as well. HPCC also provides synchronization of the localized Python execution because each node needs to execute its computations in a controlled manner, and ECL and HPCC provides a very nice platform to easily do so. And TensorFlow is providing the neural network model abstraction. It's where we build the models, and it provides loss functions and the neural network optimizers, which is what's used to process on each slave Thor node locally. And again, the reason why we use TensorFlow is because it's one of the most popular deep learning libraries. It is created by Google. It is open source maintained, and it has many, many, many of the very popular and very powerful loss functions, optimizers, and other tools that you'd need. So deep learning models, specifically deep learning models, are very large and very complex. They've been shown to produce cutting-edge results in many domains, such as image recognition, speech recognition, self-driving cars, And recently they've been shown to play against humans competitively and win sometimes in games like Go, the Chinese game Go, and it's a complex multiplayer video game called Dota 2. And to be able to do this, the deep learning models need very, very large amounts of training data. Both the size and complexity of the models, the neural network models, and the volume of the training data that needs to be processed makes the training process very, very computationally expensive, and it can take hours, days, or even weeks to train these models effectively. To do so, most researchers are using very large supercomputers, a shared memory supercomputer, multi-GPU systems, and current work is done on. My current work is aimed to provide a cluster system for these deep learning, training deep learning models, because a cluster system such as HPCC is built off of off-the-shelf components and is much more widely available to most researchers who aren't Google or Facebook that have billions of dollars. So, quick background on neural networks. The image to the right, on the top on the right, is a visualization of a very simple, fully connected neural network. It has two hidden layers. They're fully connected, and it has a 3-class output. So it'll be either 1, 2, or 3. The class 1, 2, or 3. Each neural network is comprised of neurons. Those are the circles, and the connections between the neurons, which are the arrows, are represented by numeric weights and numeric biases. The weights get updated through the training process to produce an overall model that can process the input data, which goes in the top input layer, and have an output that is meaningful. For example, a image recognition neural network model will take as an input, say, the pixels of an image, process each pixel based off of the weights, and the output could be, say, we're doing a binary classification of whether or not an image contains a cat or a dog. So the image of either a cat or dog will get processed through, and the output will either be this image contains a dog or this image contains a cat. And the model would be much more complex than what we see here. So in the training process, there's a forward pass. The data, in our example, an image, the singular image is fed into the network, and the error is calculated. The overall network error is calculated with respect to that particular piece of data. Then the second step is the backward pass. The error is then propagated backwards from the output layer and then sequentially backwards until the very first hidden layer. And each gradient, the gradient of each layer is calculated, and then the weights are updated to minimize the loss with respect to that piece of data. And when I say minimizing the loss is a mathematical representation of how well the model is doing, its goodness of the model, and it slowly tries to get towards a minimum, which is represented by the image on the lower right. That would be a simple representation of the loss of a model with respect to some data. So parallel deep learning or any neural network training, there's two paradigms. There's a data parallelism paradigm and a model parallelism paradigm. My work focused on the data parallelism, which is represented by the image on the left, and the model parallelism is represented or shown in the image to the right. I'm just covering that for completeness. Either of these can be made in a either synchronous or asynchronous approach. I went with synchronous, and specifically I modeled my runtime after parallel stochastic gradient descent using data parallelism. Okay, so ECL and HPCC handles the quote-unquote data parallelism part of the runtime. It takes the data and splits it up and passes it on to each node. The PyEmbed plugin handles the localized neural network training using Python and its libraries. And again, the implementation is synchronous and is a data parallelism. It follows the data parallelism paradigm. However, the way I implemented it is not limited to using specifically stochastic gradient descent at a localized level. It can use really any optimizer that is provided by TensorFlow or Keras. And furthermore, the implementation uses Keras, which is essentially a deep learning API for TensorFlow. It does two things. It makes the code much shorter and easier to understand and quicker to build, but it also can easily switch backends. So there are other competing libraries to TensorFlow. Keras works with them, and you can very quickly, with the change of a configuration file, just say, oh, I want to use TensorFlow, or I want to use some other backend without any change to the code, which is quite nice. So real quick, this is TensorFlow and Keras. On the right-hand side is TensorFlow code. Both of these are written in Python language. These are just the libraries. It might be kind of hard to see on your screen, but on the right-hand side is the TensorFlow code and to create the same model that is created with the Keras code on the left. And you can see, just by looking at it, it's quite a bit smaller and easier to understand and quicker. So the implementation, ECL and HPCC partitions the training data into n partitions, where n is the number of slave nodes in the system. That data is then distributed to each node along with the Python code. And the Python code is encapsulated into the PyEmbed functions using the ECL plugin, which provides a bridge to the TensorFlow runtimes locally on each node. ECL also distributes this code onto each node, along with some metadata that you would need, or that the system needs, as well as the neural network model that you abstract in the very beginning part of the process. The PyEmbed portions of the implementation, now there's functions on either side, ECL side, specialized records, record formats, and Python functions that act as interpolators between ECL records into Python objects and back again, so that the data lives in ECL in a standard record, and you just call it like any other ECL function. And I've created functions to transition to TensorFlow and then back again. Anyway, so the Python code receives the parameters, the time of execution, which would be the model, the data only on the first pass, and any metadata. It then builds a localized neural network model from the model input parameter. Recall this is an iterative process, so that input iterative and recursive, so that input model changes after each epoch. And an epoch in machine learning is one pass-through of the data. It then trains that slightly updated neural network model on its partition of data, and then once it's done, at the end of the epoch, it will then return the updated model weights to the master Thor node for aggregation. It does not return any of the data because it does not need to, and it reduces communication costs and makes it go quicker. So this is a quick code example. Starting from the top, very simply, you just distribute the training data, and you create with this function called create model. It's a Python code. You declare and abstract your neural network model using Keras, and then it outputs it into a model rec. Then the epoch step, which is recursive, will then take the it'll create the weight updates after aggregating all of the individual nodes' weight updates. And the whole process loops back on itself until the desired number of epochs has been reached. As you can see in the bottom two lines, model generation, that is a trained model that it can be either consumed in production or it can be put through an evaluate model function, which evaluates the model on unseen test data, and it will give you an output, a performance output. How well did this model train? So the case study, we used very big data, 3.6 million records long. Each record is about 850 bytes. We split it into an 80-20 split. So from now on, the rest of the presentation, all of the data sets will be of this 80%. And then that 20% was used for the test training. We used 10 different data set sizes. There they are right there, from 1:1 to 1 to 2,000. And they range from 2,240 records to 2.2 million records of about 2 megabytes to 2 gigabytes in size. When I say 1:1 or 1 to 50 or 1 to 100, that's the class imbalance ratio. And we'll touch on that in a minute. But basically, you just add those two numbers up, and that's how many thousands of records or how many hundreds of records. Each of these data sets were then run on 5 different cluster sizes with 1, 2, 4, 8, and 16 nodes. And just as an aside, the cluster was a cloud-based cluster, very small instances. They were 1 CPU each, and they had 3.5 gigs of memory, and every single slave Thor node had its own logical computer. So there was no more than 1 Thor node per machine. So these are the results. On the left, please note that the Y scale is logarithmic, and on the right, the scale is linear. And you can see its training time in seconds compared to training data set size in thousands. And each color line is a cluster size. And on the right-hand side of each graph, you can see the color corresponds to either 1, 2, or 4, 8, or 16 nodes in that cluster. So, for instance, on the left-hand graph, the purple line, you can see it's very flat and then curves up. Only after it gets to a sufficient data size, those 16 nodes produce quicker training times than, say, any of the other nodes. And this is due to the communication overhead of the 16 nodes. You know, in the 16-node system, there's 16 nodes that have to aggregate, and there's a lot of communication time. And if on a small data set, it might outweigh the performance gains of increased processing power. And then on the right, you can clearly see as the data sets get very, very large, the higher the nodes, the better, the flatter the curve. Second case study we did looked at the resulting model, the resulting model's performance. The same model was created on the same data on each different node, and we compare, does a model trained on the same data have enough, is that affected by the number of nodes? For instance, on the very top, you'll see that is the data set 1:1, and that red line is the relative performance of the model with respect to the number of nodes. So on the left-hand side, going to the right-hand side, you can see it increases. So what this means is on the data set size of 1:1, which is a balanced class, has a balanced class ratio, the more nodes actually increases the performance of the resulting model. You can't see it here quite so easily, but nodes with 1 node, 2 node, and 4 node are each better than the previous. Nodes 8 and 16, or clusters with 8 and 16 are statistically the same as the node with 4. Now, all the other data set sizes do get affected more heavily, and a lot of that is because they are they have a very high class imbalance. So traditionally, the data sets will be balanced, and the larger the data, the better the model will perform. All other things being the same. But in this case, the bigger data sets had extreme class imbalance, so the results are a little perhaps counterintuitive. So future work would be an improved data parallelism, is what I'd call it. My implementation assumes each Thor node has its own logical computer. Systems where you have multiple Thor nodes on a logical computer and multiple logical computers in the cluster would need to be addressed. Another one would be model parallelism. I only did data parallelism. A model parallelism approach would need to be worked on. And then once that was completed, a hybrid of model and data parallelism could be completed. And thirdly, would be the asynchronous parallelism. My implementation uses synchronous. So between each epoch, each wait update from each node waits for all the other nodes to finish before it updates the center model. In asynchronous parallelism, every time any slave node is done processing even the smallest amounts of data, even like a single image, it will update the weights on the main model and receive the new model. Now this has a very high number of times it has to communicate through the network, which is fine for like a shared memory supercomputer, but HPCC is a cluster system, so it probably would have to, that would be a very big concern. However, on a system that had multiple Thor nodes on a single logical computer, that would act kind of like mini supercomputers, so you could kind of combine all of these in the future. So in conclusion, I showed that I had a successful implementation of a synchronous data parallel deep learning algorithm based off of the parallel stochastic gradient descent. I presented the case studies that validates it across cluster sizes and data set sizes. I started a new HPCC library and provided possible research avenues for future work. One last thing that I forgot to mention, which is quite important actually. On this slide here, on the left-hand side, it's very hard to see from this line graph due to the scale, the Y scale. However, the smallest data set size that benefited from an extra node was only 1 to 5. Now, the 1 to 5 data set, remember, is about 6,000 records. That's only 6 kilobytes in size. It trained faster on a 2-node system than it did on a 1-node system. So this implementation, you can realize some training time performance gains pretty quickly. You don't need too much data to start, throwing nodes at it to train quicker. That's all I wanted to say on that. And my final poll question is, what roles do you see HPCC filling in the future in the domain of deep learning? You can answer on your screen, and we will go over that in a minute. Thank you. Lorraine?
Thank you, Robert.
All right.
Oh, there you are, Jessica. Thank you.
Thank you, Robert. All right. So while you take a moment to review the questions from the audience, we're going to step back to the results of your first poll question. For those of you in the audience, if you have a question for Robert, please go ahead and submit it now so he can take a peek at those. All right, so your first question. If you use machine learning, are you using HPCC systems for building models? So 42% of you have said yes, and 57% of you say that you don't use the machine learning today. But 0% said no, so that's good. So for those of you that are using machine learning, we're glad that you're able to use HPCC systems for that. All right. And if we take a quick moment to look at the questions from the audience. So here's one. Are you ready, Robert?
Yes.
All right. So the first question is, does HPCC system server-side require an NVIDIA card to support TensorFlow library?
No. The current implementation is independent of NVIDIA and CUDA. So the implementation that I presented is all via CPU. So the answer to that question is no. Now, the second question, well, I'll let you go ahead and read it, sorry.
You can go ahead, Robert.
Okay, yeah, sorry.
Ahead.
It's just, it was a nice parlay into the next question. So the next question is, does each cluster have the whole data set, or the data set is randomly split and distributed to each cluster? Do you plan to test your implementation on GPU clusters? Thank you. So does each cluster have the whole data set? Well, the cluster has the whole data set, yes, but each individual slave node does not. So if there's a 10-node system, 10 nodes in the cluster, and each node would only have 1/10 of the data. And is the data set randomly split and distributed to each cluster? Yes, it is. However, the distribution of the whole data set needs to be maintained. So if say you have a 10-class data set with each class equally represented, when you distribute it across your system, each node's partition would need to have the same distribution of that class. So each one of the classes would be equally represented. And do I plan on using GPUs? Well, that's a good question. I would very much like to, and that's a very good idea. So thank you.
All right, perfect. Looks like we have several other questions that are coming in right now, Robert. I'll let you take a look at those while I look at the results of your last poll. So the question of your last poll was, what roles do you see HPCC systems filling in the domain of deep learning? So this is kind of an interesting response here. 66% said data pre-processing tool, which is fantastic. And then the other third selected working with multiple deep learning libraries to fulfill all aspects of deep learning. So we had two answers there that were fairly popular. All right, so looking back at the questions, let's see. So Robert, what was the biggest challenge in your project?
The biggest challenge in my project would be the integration of ECL and Python specifically. The debugging was very challenging, and just having to code in two very different languages at the same time to accomplish a single goal was definitely a big challenge, but it was very rewarding once everything started to fall into place.
Oh, good. All right, and here's another question for you. What are the benefits of combining HPCC systems and TensorFlow?
So the benefits of combining HPCC and TensorFlow is TensorFlow is very, very popular. It's open source. It's maintained by many people, thousands of researchers at Google and also not at Google. So combining them, any update or any improvement to the deep learning libraries that we put into TensorFlow would immediately be available to this implementation, which would, that's just great.
Okay, wonderful. All right, so it looks like we have time for one more question here as we approach the top of the hour. The question is the implementation dependent on TensorFlow? What happens to the work if TensorFlow suddenly becomes obsolete or otherwise unusable?
Okay, so this is a good question. There's two main reasons why I used Keras. One is it's quicker and easier to write TensorFlow code. But to answer this question, implementation would not be affected if TensorFlow somehow disappeared tomorrow. Keras can quickly switch the backends between TensorFlow and some other competitors, which I can't remember the name of right now. I think Microsoft makes one, I think CNTK. You can switch between the backends very easily without any modification to the Keras code. So the answer would be no. It would not be dependent on TensorFlow's surviving.
Okay, good. Thank you so much. Robert, your presentation has been fantastic. We really appreciate you being here with us this summer and for your presentation.
Oh, thank you very much.
All right. So again, I'm going to pass everything over to Lorraine so that she can introduce our next summer intern.
Thank you, Jessica. So now we're going to meet the youngest member of our 2018 intern program. Aramis Canales is a high school student at American Heritage School of Boca del Rey in Florida. He is the lead programmer on the school's robotics team, which demonstrated their autonomous golf cart at our Community Day Summit last year. Work continues by this team on an autonomous agricultural project. And Aramis's intern project will provide them with the means to process the data collected from the various sensors around the vehicle. It's a great project which is sponsored by Ty Donovan, who is the robotics director at Aramis's school, and our HPCC Systems colleague David DeHilster, who is mentoring Aramis throughout this internship. So I'd like to welcome Aramis to our Tech Talk webcast and hand over to him so we can hear about his achievements.
Hello, I'm Aramis, and I'll be giving a presentation about my project and also a bit about the agricultural robot project that we're currently working on in our robotics lab at American Heritage. So to start, I'll give a bit of a background for my project. So in the field of robotics, there are a lot of sensors that are used in just about every mobile robot and static stationary robots. And typically, a robot will collect data from it throughout its entire runtime, and most robots tend to be used more than once. They're not just one-time use tools. So you end up with large volumes of data, and if you want to use this data effectively, you have to have a way to analyze it. So this is where HPCC Systems comes in. It can process big data, and it does that really well. However, you need a good way to ingest the data from these sensors. So that's where my project comes in. It provides an API for ingesting data into HPCC Systems, and it's open source, and it's available to anyone who needs it. So before we get into the bulk of the presentation, I'd like to raise a quick poll. Have you ever worked with the Robot Operating System, abbreviated as ROS? It's a software platform that's used in many different robots across many fields, and it's also used in the agricultural robot, which isn't in the next slide. So to collect data for testing, the developments of my project, I've been using sensors in the lab that also are going to be used in this agricultural robot. And I've mentioned it a few times earlier. It's a robot that's going to collect soil samples and other data inside a field. It's going to collect data from GNSS receivers, so it'll be kind of like the GPS coordinates you get on your phone. A scanning rangefinder, infrared cameras, samples, and it'll also be open source and will involve data analysis. It's going to autonomously drive down rows in a produce field and collect data from the sensors listed in the previous slide. And there's also a virtual reality component, but that's not as related to data, so I won't go too deep into that. Here you can see a few pictures of it. This is taken last week. It consists of two identical chassis linked to each other, one leading and one acting as a trailer. So in my project, I'm covering a few different types of sensors, most of which are listed slides ago. So here's an example of this data. If you look to the right, you can see a small visualization I made. It's has the points returned from the GNSS sensor, and they're linked together based on their timestamp. So you can see that it's really chaotic in a bit, and that the location floats around, even though, as you can see in the picture to the left, I'm standing still. So one benefit from being able to analyze the data on a large scale is that you can apply different algorithms and other techniques to this really noisy GPS data to help determine the true position of the antenna. So if you look here, the GNSS sensor I used to collect this data was the SwiftNav Pixie. It's a module we're using in the agricultural robot, and I had it on hand, so I made use of that. And with my project, I was able to collect data from the sensor after it was published through Robot Operating System. I went to ECL Watch, used the ECL modules I wrote for the project to process the records and also index them. So if you look at the image below, you can see the record structure of the GNSS data. Next is data analysis. So the big data you might collect from robots will include GNSS coordinates, images from cameras. Those tend to be quite large, and also point clouds from scanning rangefinders, which may contain even millions of points. So some of the most common applications of this data would be applying machine learning algorithms to the data collected. And as you might have seen in Robert's presentation, machine learning typically uses lots of data, so it benefits from being done in HPCC systems where it'll be much faster than running it on a single computer. And you can even take the computed weights and biases from the machine learning algorithms and run them locally on the robot to perform the classification or regression in real time. Next is the infrared camera. So if you look at the picture here, it's just a single frame from an infrared camera taken during development. What's pictured is a robot chassis. If you look to the area with most of the heat, that's just the processor. So you can kind of see this is what's going to be received by the robot. This was taken with a FLIR C2 infrared camera. And the way I did this was I wrote a package in ROS that used OpenCV to read the images. OpenCV is a open source image processing library. And then I used two more open source ROS packages to the images into messages, which I then gave to the ROS package I'm writing as part of my project to ingest it into HPCC systems. This is the resulting logical file. So one reason it's helpful to have this available for camera data is that if you look to the record size, for just 593 records, that's probably a few minutes of video. It's taken 136 megabytes. So with a robot that runs for much longer than 2 minutes, this can get really large, and it benefits a lot from having it available on HPCC systems. As for publishing the project, there is a repository containing the ROS workspace, and with ROS you can use C++ or Python to create your packages, and there's also a subdirectory inside the workspace containing all of the ECL modules I wrote. So this is just an example of some of the code that you might write in ROS. This is the Python implementation of the code used to convert the laser scan messages from a scanning rangefinder into something that can grade into through ECL Watch. And here's an example of my layouts used in ECL to contain the records for all of the sensors that I implemented. So before we end, I'd like to raise another quick poll. What roles do you see HPCC systems filling in the field of robotics? So finally, analyzing data isn't in the scope of this project. We're mainly dealing in collecting the data and having it available for analysis. However, it would make for a good continuation of this project. For example, collection of data from the agricultural robot or some other robots that make use of this project, and then conducting the analysis of the data and possibly porting that analysis from HPCC systems to a local machine robot. And thank you.
All right, Aramis, thank you so much. I just want to make sure that everybody on the webcast today noticed that Aramis is a high school student, so we're actually very impressed with your results, Aramis. All right, so I'm going to take a moment. I'm going to review your first poll question. While I do that, take a look at some of the questions that are coming in and prioritize those for us. People in the audience, if you have questions for Aramis, please send those in so that he can take a moment to review those. All right, so on to the first poll question. It was, have you ever worked with a robot operating system, ROS, the platform driving many robots in education, research, and industry? So right now it looks like 80% said they haven't, and 10% said that they have not heard of it. So 10% if you have. So that's awesome. We're glad that our community is getting involved with some of the robots there's so many amazing ones that are out there today. All right, Aramis, we're going to go ahead and take a look at the questions. Are you ready for your first one?
Yes.
All right, perfect. So the question is, what computer language do you use when creating ROS packages?
When creating packages for ROS, you can use C++ and Python. Those are the two officially supported languages. However, there are also unofficial ports for Java, Lisp, and a few other languages if you're interested. I don't know them all at the top of my head, but
that's okay. That's enough to get us started. Thank you. All right. So here's the next question. What kind of computer or motherboard is on the autonomous agricultural robot?
On the agricultural robot, there's a RoboRio and also an NVIDIA Jetson TX1. The RoboRio is something we use in FRC, first competition, to control the robot, and it's being used to interface with all of the hardware, like the motors, motor controllers, along with a few of the sensors, and also to receive commands from the external driver station. It's what we use to turn the robot on and off. As for the Jetson TX1, it's a single-board computer developed by NVIDIA, and we're using it to run the packages written for the robot on the robot operating system and also handle some of the heavier lifting, like combining data from all the sensors and also doing things like localization or mapping. I wrote more about this in a blog post. It should be linked under attachments and links.
Great. Thank you. Thank you. All right. Let's see. Here's another question that's come in. How do you compare ECL with the other languages you've learned? Were there any challenges that you encountered in learning it?
So I think ECL is really not too similar to most other languages I've learned because I don't have any prior experience in query languages, and I noticed that was a large part of ECL since it deals with large amounts of data. So I think that was a challenge in learning it, getting used to mostly the structure of it since it's really different from most action-based programming languages, I guess, since it's, for the large part, based on declarations.
Okay, thank you. So here's another question that's come in. What inspired you to work with HPCC systems and ROS? Is anyone else doing this?
I was inspired by my mentor to work with HPCC systems since there's not any others. Well, there's no one else doing it, so it would be good to create something that would allow who wants to do it easily.
All right, fantastic. I'm going to go ahead and take a moment and go back to your last poll question. The question is, what roles do you foresee HPCC systems filling in the field of robotics? So our choices were big data and autonomous control. 50% thought big data, and 50% thought it would be both areas. So very interesting. That was a very good question. All right. Here's a quick question, Aramis, that came in. Is your library in a ROS repository? And would you be able to provide us with a link? We could probably put that in our blog if there is one.
So my package is in a ROS repository, and I'm planning on publishing it through GitHub and also through the ROS build farm. At the moment, I don't have a link. However, really soon I will have one, and I'll probably publicize it through my blog, which is linked here.
All right, fantastic, fantastic. And we'll work with your mentor to make sure that maybe we're able to take and put that out on the blog and make sure that we're publicizing that for other people. All right, Aramis, thank you so much. We really appreciate your spending your summer with us. All right.
Thank you.
So, Lorraine, I'm going to go ahead and turn it over to you to introduce our next presenter.
So, Saminder Vijayaratne has almost completed his internship with us. In fact, his last official day with us is tomorrow. So I'm very glad that the timing of this tech talk provides us with the opportunity to hear from Saminder about his MPI proof of concept project. What we wanted to achieve here was to compare the industry standard MPI system with our own version, which we created when we started our big data platform in the year 2000. And back then MPI was considered to be quite unstable, which is why we built our own. But now we want to know how the two compare. So Saminder has been helping us work towards finding the answers to the questions we have. He's been working alongside our HPCC Systems colleague, Mark Kelly, who is an expert in communications protocols, and also Jake Smith, who is our Thor expert. They've been following his progress with great interest and supporting him as he worked towards producing the findings and recommendations that he's about to share with us in his presentation. So welcome, Saminder.
Thanks, Lorraine. In this short presentation, I will be explaining to you about the main focus of my summer intern project surrounding a project called the MP Library inside the HPCC platform. So this poll question is relating to that. How long ago was the current implementation of the MP Library was introduced to the HPCC platform? Please go ahead and poll for the nearest answer in your presentation screen. So I'll dive into the presentation. This here is a very abstract view of the HPCC platform, which you may have seen in the wiki. You have several components here working together to harvest, filter, analyze immense amount of information in the hopes of facilitating millions of queries to retrieve the relevant data. However, to give you a quick understanding of the project, we will only focus on the Tor component of the HPCC platform. Zooming into this component, in a real run, the Tor performs massive communications with different components, and these components are represented as separate applications. And given a single component, each component will have multiple applications. For example, the Tor will have one master node, but it can have several slave nodes. Each component would have such separate process in order to distribute the workload and perform massively parallel tasks in order to achieve their own final goals. All this results in needing to have a parallel communication framework. That means a very solid backbone of communication for each of these applications to exchange their workloads and their results. In HPCC system, this framework is called the Message Passing Library, or MP library for short. So what is this Message Passing Library? This library, created nearly 2 decades ago, is designed in the hopes of being a generic framework that would allow a process to reliably and efficiently communicate with another component independent of the underlying network. The current library is designed to have a similar interface to the MPI framework. If I remember MPI 1.0 version. It uses C-native socket libraries and overlays many high-level features that a parallel application would require. This complete masking of details entailed in the performing network communications by the MP library gives external components the freedom to seamlessly integrate with their counterpart process running elsewhere in the network. Let's look under the hood of the MP library. And the first thing we notice is that it exposes a very comprehensive APIs for the users. And the current implementation of the MP library implements this API using the JSocket library, which is also part of the HPCC platform. And it has a very comprehensive set of TCP and UDP protocols implemented. Now that you guys have a thorough understanding on the purpose of the MP library, let me explain what I was trying to do in my summer internship project. So as Lauren explained at the beginning, MPI was still in its infant stage when the JSocket implementation was introduced. However, MPI is now a fully fledged evolved framework with multiple iterations and versions out there that is being used by many applications that requires distributed parallelism. Hence why we are trying to see whether MPI framework could improve the massive parallel communications performance required by the HPCC platform. We, of course, have attempted this in several stages. So these are a couple of steps like introducing with the single thread mode and multi-thread, and this all has a sub-task as well. So in a nutshell, we had the JSocket implementation, which we actually call the MP implementation henceforth. So we are going to have the MPI implementation sitting alongside it just so that we can do a comparison between the two. This should seamlessly introduce MPI as a backbone communication layer for MP library that would be capable of replacing the use of JSocket library. That is, the proof of concept should also have a non-disruptive impact on the other components external to the MP library. In order to understand what is required of MPI, it would be easier to revisit what was in the MP library API, which we saw earlier. We have 3 abstract interfaces to define a component-independent messaging and routing, and another interface that defines operations that involve in this message communication. Node is simply a process running independently. This could be a Tor slave node, or a master node, or a roughly agent process. In order to define communication between two nodes, we logically bind all the relevant nodes together and call it a group. All communications will happen with respect to the nodes in this group. A message component would encapsulate the data in any form that is tagged and recognized by the process which is receiving it. And the communicator would define the high-level communication primitives important to any parallel communication network. For example, one node would want to send a message to a second node and would call the send function while the second node would call the receive function. Specialized functions like reply, send, receive are present to carry on a stateful conversation between the nodes. At any point in time, you can cancel these communications or listen to any other incoming communications. So rather than giving you details on the implementation of the API interface, which you can actually go and see, so I have provided the link for the repository I have been working on. I'm going to give you some challenges I faced trying to implement this API functionality using MPI. So although MP library API was defined to mirror MPI framework functions back in the day, since HPCC components require more sophisticated features, these API functions have an extended expectation that is not directly supported by MPI. For example, support for timeouts requires a thread monitoring the status of the communication. Multiple threads focused on a single communication would usually mean implementing a thread safety on shared data and avoiding race conditions. This is not necessarily a challenge, but does require some pre-planning and considerable amount of software engineering. However, some of the vital functionalities that would be useful are not present in MPI. For example, MPI doesn't allow efficient control of buffer space. This includes flushing of messages in the pipeline, avoid duplication of same message when buffering, and limited control on how data buffers access that forces manipulation of input buffers. One example here is that the message buffer interface contains multiple data fields which is disconnected in the memory but requires transferring, but MPI only supports accessing continuous data buffers. We had some issues due to how different MPI libraries are implementing their functionalities. At the beginning, we used OpenMPI, one of the most popular MPI implementations, which doesn't properly support multi-threading. And the MPI spec doesn't enforce a strict range for MPI tags. And this matters because the MP library tags ranges the whole unsigned integer spec, and different MPI implementations would have a different range, and it has to be positive. Another minor challenge we faced was setting up a proper testing environment and test scenarios. This is because it's not easy to replicate a real use case, because a real use case will have massively parallel communications going through. And replicating the use case plus the environment would be a challenge. Some of these challenges forced us to take different design decisions to resolve issues that would otherwise have hindered the project. We list few major ones here. So the first one, we had to use the synchronous send function in MPI instead of the asynchronous ISend or the IBSend in order to avoid creating a larger memory footprint, duplicating the data. And we ended up using asynchronous IReceive function because the asynchronous receive function cannot be cancelled from an MPI framework. We also introduced a dual message scheme because MPI cannot combine the reply tag field that also needs to be sent along with the data buffer in the message buffer on the fly without manually copying or duplicating or modifying the message buffer storage. MP library allows message tags spanning entire unsigned integer space, which I mentioned earlier. And however, MPI spec only supports positive integers along with a restrictive range. Therefore, we had to shift existing MP tags to the ranges supported by MPI tag. So we managed to resolve most of these issues and had one version of our POC in hand, and we went on with some initial performance tests. We used an all-to-all test case where each node sends a message to all other nodes. There are several parameters we considered for this benchmark test. Following results are some of the selected performance evaluations based on few of the parameters to show an initial idea on how MPI performs against the existing MP implementation. The results shown here are, and in next slide, are for running multiple nodes in the same host and repeating the communication 20 times. I will later mention incomplete results of running experiments in varying these fixed parameters. Performance here shows buffer size versus message transfer rate. The blue line shows the performance of existing MP implementation, and red line shows the MPI implementation. By introducing a dual message scheme mentioned earlier to resolve the particular issue relating to reply tag, added an additional overhead to the communication cost. Top two graphs relates to showing using the dual message scheme, and bottom two graphs shows when we use a single message scheme. We also decided to experiment and see whether use of asynchronous receive we have a performance hit. Left two graphs show when asynchronous receive is used, and the right two graphs shows the right side of the graph shows the asynchronous receive was used. We repeated the same experiment. So based on this graph, you can see that MPI is actually performing well compared to MP implementation, but this changes with some different parameters which I mentioned later. So we repeated the same experiment with 4 nodes, and now we see MPI underperforming initially. The clear observation we see here is that for lower buffer size, MPI seems to perform poorly. We need to repeat this experiment, increasing the number of nodes to see whether the break-even buffer size would increase with P. We did do a few other experiments which we have not presented here. They included putting the host system under pressure, resource constraints, running multiple nodes in multiple hosts, and increasing the number of iterations for a single test run. As of now, the results showed MPI intermittently performed well, while in general being as good as MP or poorer performance. This is a short, this graph shows that the impact of different design decisions on communication protocol. So that means if we use dual message scheme with asynchronous receive, or if we use a single message scheme with a synchronous receive or synchronous receive. While it is not a solid analysis with the limited amount of results, we can have an initial observation that one of the dual message scheme with asynchronous receive doesn't give the best results under current implementation. We, of course, have a lot more testing left to do. And based on the results, the POC should be revisited to see whether there are ways to improve it. And since this is a POC, I think at this point we are actually getting the results we are expecting from this project. However, given we actually get the chance to move on with the MPI as an MP library implementation, there's a nice spin-off project that can happen with MPI using collective communication primitives, because most master-slave communications involve in collective communication. So a quick question for you guys. Using all-to-all test cases, we can estimate within a reasonable margin of error the performance gains of using MPI as a back-end communication framework for Flowcaster. Is this true or false? Provide your poll at the screen.
All right, Suminder, thank you so much. That is a wonderful presentation. So while you take a moment to review the questions that have already come in from our audience, and to give the people that are viewing today the opportunity to submit some additional questions, I'm going to go ahead and review the results of your first poll question, which really is a little bit of a pop quiz. So the question is, how long ago was the current implementation of the MP library introduced to the HPCC Systems platform? Our choices are 5 years, 10 years, 20 years, and 32 years. So I will tell you that 50% guessed 5 years, 25% guessed 20 years, and 25% guessed 32 and a half years. So Saminda, would you like to share the answer with us? And if you don't know the answer, I have it. So, okay.
So I was told like this actually came up around, I think, early 2000s. So that's like nearly 20 years ago. And I initially thought it was actually done like 5-6 years ago, but it turns out it's much older than that. And surprisingly, it was a solid implementation when I was working with that.
Exactly. That's exactly right. I reached out to Flavio, who slipped me the answer to Flavio, and he said it's about 18 years. So it's coming up on that 20. So that's, this platform is extremely mature, very tested, and this is just another example of how solid the platform is. All right, so we're going to take a quick peek at the questions from the audience. Are you ready, Saminda?
Yes, go ahead.
All right, perfect. So question number 1 is, how would your implementation handle cases where HPCC system nodes in a cluster goes down or becomes unresponsive?
So in this case, the MPI framework, so one nice thing about the MPI framework is that it actually handles these scenarios where the node goes down or node loses internet connectivity. It attempts to revive the node, then bring it back up. So if in any reason, if MPI framework actually can't do that, it basically means something very wrong has gone down. And even in our case, we wouldn't be able to actually solve that. So I don't have to implement that. The API framework should take care of it. That's one of the very good advantages of using the API framework.
All right, fantastic. All right, so the next question is, can I use the MPI implementation in your source code repository to run Thor right now?
At the current state, you cannot. The reason is that the way the current implementation of Thor works with the JSocket implementation and the way MPI triggers starts up applications is a different variety. For example, in the current implementation, when Thor starts up, it manually starts separate processors for masters and slaves, and they need to start their own servers with the different ports. And in MPI, this is sort of automatic. You just call MPI with MPI run command and provide the applications to run and how many to run, and it will automatically start them up with their own internal ports that communicate. So this needs to be set up in a way that it's a sort of simplification. We need to do some simplification compared to what's happening right now, but you do have to do some changes. At the moment, out of the box, you can just run all the test cases in the MP library, which would represent most of the scenarios in Thor.
All right, and it looks like we've got one last question here. If you're using both the implementations, can a message coming through MPI, through the MPI implementation, be used to the MP implementation?
Yes, the current implementation supports that. We simply have the same message, we create the same message and pass it along to the MP library without knowing whether it's the MPI implementation or the MP implementation in the background. So whatever the message that goes through or comes back should work, actually will work for either implementation.
Jessica, is that all the questions now?
All right. That is the end of the questions. We're going to wrap things up, I think, with votes from the audience. And this is your last pop quiz, Minda. Using all-to-all test case, we can estimate within a reasonable margin of error the performance gains of using MPI as the back-end communication framework for the Thor cluster. So the options were true, false, and not sure. 60% have said true, and 40% have said not sure. So would you like to give us the answer?
Actually, this is sort of a trick question. It depends on the use case. It's true because if you think of the happy case scenario for the Thor cluster where like everybody communicates with everybody and sending messages, all-to-all will actually be a very close representation of such communication. But the thing is that in a real-world use case, it's not going to be this case because like sometimes the messages would actually hog in a subset of nodes and other nodes might remain idle or having less number of communications. So all-to-all will not represent such scenarios because messages can get cancelled and there might be stateful communications going back and forth between two nodes during the whole communication time, which effectively means that all-to-all will not capture the general case in a Thor system. So it's false. And if you're not really familiar with the system, not sure is also a correct answer in this case.
All right. Linda, thank you so much. Lorraine, I'm going to hand things over to you before we wrap things up, so you can share some parting words with us.
Thank you, Jessica. I think this has been a really great set of presentations, and I'd like to thank our students for taking the time to present about their intern projects today, which they've all done so very well and professionally. As you can tell, these students are all exceptionally hardworking and have achieved a lot during their time with us. It's been really great to have them join the team this summer, and I know their mentors would join me in saying what a pleasure it has been to work with each of them. We also thank them for their contributions to the HPCC Systems project. All of the things they're doing will benefit our open source project and community. And on behalf of the HPCC Systems platform team, I would like to wish all our interns every success with their continued studies. And I hope to see some familiar names among the proposals I receive for next year's program. The proposal period for those who are interested will be opening towards the end of September, with new projects available on our list, and an announcement will be made in our forum on the website when that happens. So I'm going to hand back to Jessica now to close, but thank you all for coming to listen to our students present today.
Mm-hmm. Absolutely, and to reiterate a little bit of what Lorraine said, we are just so impressed with all of our summer interns, and we thank you all so much for being a part of the HPCC Systems and contributing to our community. This is one of our most popular tech talks every year, and today's presentation did not disappoint. We had more questions from the audience for each presenter than we could even get to. So I hope each one of our presenters today understands how much they're valued by our community. And if you would like to be one of our interns, as Lorraine said, we've got information coming, and we welcome mentors too. So you don't have to work for LexisNexis to be a mentor. If you would like to be a mentor, if you're deeply ingrained with our community, we'd love to hear from you. So for future Tech Talks, we're always looking for new success stories. We're looking for new use cases. If you've got something you'd like to share with the community, we would love to hear from you. Applications, ECL tips and tricks, suggestions for the roadmap, anything, please reach out to us. We'd love to have you on our webcast. Reach out to us at techtalks@hpccsystems.com and to download our wiki for more information. All right. Thank you, everyone, for joining us today. Look for the blog for a follow-up of this presentation, and this presentation will be recorded so that you can watch it Thank you so much.